Welcome to another in our physics tutorial program. And this program is going to be a little bit different from the others because in this program we're going to take a look into the future. But it's the real future. It's not science fiction. It's the future that many of you watching this program will actually live to see. It's a future which could have enormous implications for Bhutan and for the world. And what we're going to look at in this program is something called nuclear fusion. Now, you may have heard of a nuclear bomb, you may have heard of a hydrogen bomb. A nuclear bomb, an ordinary nuclear bomb, and also nuclear power stations which generate electricity, they work by taking the nucleus of an atom and splitting it in two. And when you do that, you get a lot of energy given out. Nuclear fusion, which is how a hydrogen bomb works, is the reverse process. Instead of taking a nucleus and splitting it in two, we take two nucleuses and force them together to make one. We fuse them together, hence nuclear fusion. And this is thousands of times more powerful a process than with nuclear fission when we split the nucleus. So our guide into the future, and it's a future that you will see in your lifetime, our guide into the future is a visitor to Bhutan who is actually on holiday, and he is a tourist here in Bhutan. But he's agreed to come and talk a little bit about looking into the crystal ball and seeing the future of energy. So I'm very pleased to introduce to you Mr. Chris Carpenter. Welcome. And Chris was, until very recently, the head of public affairs at the Cullum Centre for Fusion Energy in Oxford in England. So Chris, welcome to Bhutan, and we hope you're going to give us a little glimpse into the energy future which could save the world. Chris, over to you.
Thank you, Michael. And first of all, I should say thank you to the Bhutanese people for such a beautiful country. I want to talk to you about nuclear fusion, but before I do that, I need to explain why we need more energy. We all know that oil wells are running out. We've reached peak oil. Indeed, the North Sea has gone past its peak, and it's very difficult to extract more oil from the North Sea. The same is the case right across the world. So we need to look for new energy sources. You mentioned nuclear fission. Now, we all remember what happened at Fukushima. The Japanese now have terrible problems there with nuclear fission. Nuclear fusion is different, as you mentioned, and they don't have any long-term radioactive waste and no long-term storage of radioactive fuels in the machine itself, which is one of its great advantages. So I should explain to you what it is. What we're trying to do is to build a sun on Earth, a miniature sun on Earth. Now, the sun is a fusion reactor, and all the stars that you see in the sky at night are fusion reactors. But they're very lazy ones. They burn at very low temperatures. Well, low temperatures to us who work in fusion, and that's about 10 million degrees centigrade or so. In order to make fusion work on Earth, we need to get up to temperatures far higher than that. 100 million, 200 million degrees centigrade. And I'll explain why we need to do that in a minute. And you'll say to me, but Chris, how possibly can you hold something which is, I should explain to you, is the four states of matter, because I'm going to talk about the fourth state of matter, right. Plasma.
And I should add, in school, of course, you'll probably only learn about three states of matter.
Yes, that's right.
But you're saying there's a fourth.
There's a fourth,
right.
Exactly right. So the first state of matter is solid.
Right, so this is
ice.
Solid water.
Yeah.
Solid water.
And if we were to heat that up, it turns into water. and that's the second state of matter. Heated up even more, in this kettle boiling and steam coming out of here, and we've turned it into a gas, third state of matter. Now there's a fourth state of matter, and that is when you heat it up so much that the atoms are bashing into each other so hard that the electrons get stripped away from the nucleus, and you end up with this sort of soup. And it's called plasma because it means without form. And we all know what plasma is because we have them in these low energy light bulbs.
So there's plasma inside there.
Plasma in there. There's a plasma arc inside there, and fluorescent tubes, neon signs.
So this fourth state of matter, plasma, isn't something weird and strange which exists only in somewhere far in the universe. It's actually in our neon tubes.
Absolutely,
and in our
yes.
long life light
Plasma
bulbs.
arc welding. There are lots of examples.
Yes.
Lots of examples
Yes.
of plasma. But 99.9% of the visible universe is plasma. So when you go out at night and you look up at your beautiful starry sky,
Yes.
every one of those pinpricks of light is a star, is a fusion reactor, and that's plasma that's giving us light.
And so our sun is plasma.
Exactly.
Right.
And our sun, and perhaps I'll explain to you about our sun. Our sun is a very laid-back fusion reactor. All the suns are because of their mass. They're so big. And you know it takes 500,000 years for a particle inside the sun, after a fusion process has been taking place, a very special fusion process takes place in the sun, and it takes 500,000 years before we see it as light and energy coming to us.
Right. So when we look up at don't look at the sun, by the way, do
Yes.
we? But when one sees the sun, the little fusion process that took place in that sun, it takes 500,000 years before we actually see the effect.
Exactly right.
So when we're looking at the sun, we're looking back in time 500,000 years.
Yeah, exactly right. In a fusion machine, and I'll explain how we make one of those, because you're going to say, how are you going to hold 100 million degrees? I know you can see, I can see it in your face now, but I know you're going to ask me that question. But in a fusion machine, the amount of time that we can hold it for is about 1 second.
Right.
So everything has to happen a lot quicker. So that means you have to put a lot more energy in and make it happen a lot faster in order for that process to take place.
Yes.
Now, we can't hold something for that long in one of our fusion machines, so we have to make it hotter, so everything happens quicker. So that's one of the tricks to fusion. So I've explained it's a plasma, and these particles now have the electrons are separated from them, so they have a charge. They're positively charged because the electrons are negatively charged.
Right.
So these have a charge, and when
So these are positively charged because of the apples.
yes,
The apples are protons, and
Yes.
they've got the positive charge.
charged. Yes, this has got the charge, and you try and push them together, rather like me trying to push these two north poles of magnet together like this, and I try and push it together, and there are resistive forces, and I have to use a lot of energy before I can actually push them together.
Yes.
You can try it at home. So that's what we have to overcome. That's one of the reasons why we need to get up to these high temperatures, because we've got to give them a lot of energy so that they will collide. And what I'll do is, at this point, I'll show you the fusion process, because I think it fits in here quite nicely. So as these come towards each other, first of all they miss, and then we try again, and you imagine there are millions and millions and millions of these in the machine, and they're coming together, and all of a sudden they'll fuse.
Right.
And what happens then, to get it the right way around, is that we make helium. So this is
this produces helium there. Yes.
and a spare neutron.
Right.
This is helium, and it still has a charge. And we'll remember that because when I explain in a minute about the machine. And this is the neutron, and this has a lot of kinetic energy.
So that
huge
comes
amount.
flying out.
It comes flying out, and that'll be captured on the outside of the machine. And when I explain about how a machine works, we'll go into that part. But let's take it step by step.
So could we think of that as a Maruti Alto and a truck coming along the expressway, and having a head-on collision,
yes.
and a headlight flies
Yes,
way up into the sky
with a lot of energy.
with a lot of energy.
A lot of energy. So how do we do it? Well, we do it in a special sort of machine, something called a tokamak. Tokamak is a Russian word. It means
Right.
toroidal magnetic chamber.
Can we say that again, Chris?
It means toroidal magnetic chamber.
right, a
And
toroidal.
yes, now I'll
Right.
explain toroidal. Toroidal is the shape.
Right.
So it's like a lorry tire.
A donut.
A donut, exactly
Yes.
right. Yes, a donut. It's that sort of shape. And it's that shape for a reason. And this was discovered in Moscow in the late 1960s. But you know, the fascinating thing about fusion is that the whole world has been working towards fusion research since the middle 1950s.
Right.
There have been no secrets. It's sat above politics, above everything else. And even, you know, during the heights of the Cold War, my previous boss...
Which was the time when Russia and America,
Yes.
or communism versus the West,
Yeah.
all sorts of tensions.
All
yes.
sorts of tensions. My previous boss was actually working in Moscow for a year.
Really?
And
Yes.
the Russians are on it, and he was making some very special measurements to measure the temperature of the plasma.
Right.
And the Russians couldn't have done it without the work
Yes.
that the UK was doing.
So it is very interesting, isn't it? Just on a political level, politics is there, but there's an awful lot goes on underneath that we don't always read about.
Yes.
And what appears to be total enemy sometimes can be cooperative friend.
Yes, that's true. And when I tell you about the future and about the collaborations towards the end of this talk, you'll see that how the whole world is working together to make fusion work, and that's quite really impressive. So let me explain the machine.
I'm just going to use your second state of matter.
It's fine. You've just drunk about and enough fuel to keep you in all your energy needs properly for, I don't know, 3 or 4 months. But anyway, we'll come to that
We'll
later.
come to that.
So, toroidal. So we have this donut shape. Oh, well, first of all, the first fusion machines were actually just long tubes. Now, I was going to say, how do we hold the plasma in there? And you remember I told you it has a charge.
Yes.
That charge, those particles are affected by magnetic fields. And we all know, we can all do a simple experiment with the magnets and the iron filings. So if you what we'll do is we'll put a magnet underneath this paper, and we'll shake some iron filings on top.
So this is the sort of thing one does in school.
Absolutely. And what you see there is you see the plasma.
Right. And the plasma is this mess here.
Yeah, exactly.
The
These
two
are all
protons and the two
yeah,
neutrons.
and they're all moving
Yes.
around at the moment, quite just moving around quite
Right.
randomly in there. Once you put a magnetic field on, they start spinning around the magnetic field
Right.
lines. Now, another special thing about plasma is that you can actually pass a current through it. That's why you get light in here.
Right.
So when you pass a current through it, 2 things happen. One is that it forms a magnetic field of its own, which pulls the plasma onto itself. So
So it makes it collapse even more.
makes it collapse into itself. And the other thing is it heats up by resistive heating. So,
Right.
so
Just the way an ordinary electric fire.
just like exactly. So 2 things happen. You start heating the plasma, and you also contain it. You start holding it away from the walls. And lots of work in the early days of fusion was done on just these linear machines, just long tubes.
Right.
But it doesn't take a rocket scientist to see that you've got a problem at the end,
Yes.
because the particles hit the end walls and lose all of their energy, because we only have a tiny amount of fuel in there
Right.
at any one time. So the answer is to get rid of the ends. You bend a tube round on itself and you've made this torus.
Right.
And that's brilliant for fusion design,
Right.
because what you can do then is you have a torus, and then you have a primary winding through the middle. And the plasma, because it's conducting, can be the secondary circuit of a transformer.
The transformer.
And you can pass a current through there. And the machine that I worked on, JET,
Yes.
can
What does JET stand for?
stands for Joint European Torus, which
Right,
is a
right.
European-funded experiment, which is at Culham.
Right.
And that machine, you can pass 30 megawatts or so of current through the plasma, and it heats up.
And
it
that's
heats
the
up.
output from one of Bhutan's small hydroelectric power stations, the
Yes.
total output from it,
Absolutely.
through
yes.
this little...
Yes, and that's only one bit
Yes.
of the heating, but I'll tell you about it.
Yes.
And then what we do is we so we've got a transformer in the middle, and then we superimpose on other magnetic fields by putting coils around the
Right.
outside, and you make a complicated cage in which to hold the
Right.
plasma. And effectively, you've held the plasma in this magnetic cage. Now that's
So
not
it's a bit like, actually, if we look at the fruit here, it's a bit like making a wickerwork basket out of bamboo,
exactly.
but shaped like a donut which holds the fruit in there.
Yes, and now I'm going to add something else.
Yes.
Then try and fill it with jelly,
Right.
a lot of jelly. And what would happen if you did? If you
Well,
tried
I
it?
think probably my grandson would eat it all.
Will it squeeze? It would squeeze out of the holes, wouldn't
Right.
it? And then
It
you
would
could-
indeed, yes.
So you have to find some way in which you can stop that happening.
Right.
So this has to be a very complicated shape in which you can
Right.
hold it.
Right.
So we've done that. And by the time you've passed this current through it, it'll get up to 15, 20 million degrees centigrade or so.
Now
And
you
that-
say that, 15 or 20
20,
million
and-
degrees, as though that's a bit cold.
It is. It's not hot enough for
Really?
us. So as you remember, I said we needed to get up to 100 million degrees centigrade or more. And so the second way of heating it up is by, we have a second way is by beaming in particle beams.
Right.
And cappuccino coffee maker is a good way to describe it. You know, if you have a frothy coffee,
Yes, yes,
you blast superheated steam through the milk and you make it hot and frothy.
yes.
We blast superheated particles into the plasma, and they give up their energy by collision, and they heat it up. And
Right.
that way we can get it up to these higher temperatures.
Right.
And then a third way is to beam in microwaves, rather like your microwave
Microwave
at
oven,
home.
yes.
And you beam microwaves and they spin up the
Yes.
nucleus in there.
Yes.
And by doing that, we can get to between 100, 200 million degrees
Yes.
centigrade.
And one really does need to think about what 200 million degrees centigrade means. Our boiling water, which hurts a lot if you spill it on
Yes.
you, is 100 degrees centigrade.
Yes.
So you just try and think of 200 million degrees centigrade.
Yeah.
That's pretty hot.
Yes. And we not only do you need to do that, but you need to hold those particles
Yes.
there for long enough, and you also have to have enough particles there. So that's something called the triple product, and that's the goal,
Right.
if you like, the aim
Yes.
of fusion. If you can have enough particles there, you can hold it for at least a second, and you can get it to over 100 million degrees centigrade,
Right.
then you've achieved fusion, and as long as you put more fuel in, you can get the fusion process taking place and these high-speed neutrons coming off, which you capture on the outside.
Right. So just to recap, when the fusion happens, we get helium nuclei.
Helium nuclei,
And an orange, that's to say a neutron,
And, yeah,
comes shooting
shooting
out
out.
with very high energy.
with very high
Right.
energy. Exactly right. So what we've done is we've turned hydrogen into helium, and that's exactly the process that takes place in
In
the
the
sun.
sun.
Yes. So where have we got to? I've talked about the triple product. So where have we got to in progress? What have we done in the
Yes,
world?
I mean, I was going to say, if I
I
can
mean-
interrupt you, all these ideas are all very well, but I said we were going to be looking into the future. Is it a real future? Has any of this actually gone beyond just theory and thinking about apples and oranges? Is it real yet?
It is real yet.
Right.
JET in 19 82 and 88 ran using the real fusion fuels.
Right.
I should explain about how JET about the way JET was set up first of all.
Yes.
I think JET was set up as a joint European project after the oil shock in the 1970s.
Yes,
So
so
a
for
lot of
anybody who wasn't alive in the 1970s, in 1970 there was a sudden, enormous increase in the price of oil. Now, if you think that what that means for running a truck or running a car, that caused a very big economic shock, especially in the West. I don't know that in 1970 it affected Bhutan much because there were only about 50 vehicles in the whole country, but certainly in the West, a big shock.
So Europe invested a lot of money, and they decided that and the other thing I should explain, big is beautiful in fusion.
Right.
The bigger you can make the machine, the bigger the plasma is, and the bigger the plasma is, the more thermal insulation that plasma gives to itself, so it's easier to keep hot. It's like putting extra blankets on when you're cold, or your blanket, or wrapping yourself up. So the more insulation you can get because you make it bigger and bigger and bigger, the more efficient it becomes. So there had been tokamaks, these Russian design, originally Russian design, but it was very quickly picked up in the West. We built them in France, Germany, in America, in Japan. So right across the world, in China, they were being built. But they were all relatively small, so they couldn't get up to the high temperatures needed because they didn't have that thermal insulation.
Yes.
And JET is, as I said, the world's biggest machine currently, and it has operated in tritium. And when it operated in tritium, it got out 18 megawatts of fusion energy.
Right.
That's 18 megawatts of those neutrons coming off. Yes. But it took around about 32 megawatts to get that 18
So you
megawatts.
were actually putting
more energy
than you got out.
More than got out.
Yeah.
But the reason for that is because JET was made with just ordinary magnetic coils, ordinary copper coils around it. But JET's still operating today. And because theory has improved, and we've looked at the way that you hold the plasma and what little tricks you can, what little bits of magic that you can do with tweaking these magnetic fields so they become exactly the right shape.
So this is a very good example of where theory and practice actually come together.
Absolutely.
You know, sometimes we learn all about theory and it just stays as theory. But if one starts to actually do it and use it, it becomes technology.
Yes, and you see in JET, I mean, it's fascinating to go into the control room there, and you see people from all over Europe, and then there will also be people from America and Japan who would come on secondment as well. So you get this truly international feel.
But you don't have a Bhutanese there yet.
No, we don't. I don't
So
think.
if only we could produce a good physics graduate from Bhutan, you may one day end up working at Culham.
Or more importantly, on the next machine, which we'll talk about later.
You'll get on. Yes.
But what I was going to say, not only is it international, but you have a mixture of theoreticians and experimentalists working so closely together. And we wouldn't have got to where we are now if it hadn't been for supercomputers to be able to model the way that the plasma behaves, because you can imagine it's such a complicated shape, can't you?
Yes.
So JET has produced fusion energy, and it's demonstrated that fusion, you can fuse these together, produce the neutrons. We haven't produced electricity, it's not designed to. All we have is about 120 different diagnostics to tell us the temperature of the plasma. I might mention that actually. How do you measure the temperature of the plasma?
How would you actually measure a temperature of 100 million degrees centigrade? No point sticking a little thermometer into it, it might melt. So how do you measure it?
Well, actually, you say that. If you put a thermometer in it, actually, the plasma would go out. probably,
Oh, right.
rather than the thermometer melting, because there's only a tiny amount of gas in
Right.
there. The volume of the vacuum vessel, this torus shape, is about 100 cubic meters.
Big.
And we pump it out. We take out all of the gas, so it's a very high vacuum. Then we puff in a tiny amount of gas, and the amount of gas, the mass of gas that we put in there is about 100th of a gram. That would be one of your lovely Bhutanese postage stamps worth of mass, if you like.
Right.
So the amount of fuel you put in there at any one time is tiny. So, and it fills up the whole space, and that makes it easy to ionize.
Right.
So you can't have too much in there, or else it would, like bursting a balloon, really.
Yes.
So
yes.
because you're only holding it by magnetic fields.
Right. Right.
So it only uses tiny amounts of fuel at any one time. So that's JET, and JET's been really, really successful. So the next stage is to build a machine twice the size of JET. That means it's 8 times the volume. So it's 800 cubic meters. So it's a huge machine. You can drive a car through the middle of it, of the torus. It's that big. And that's currently being built in the south of France. And it's called ITER, International Thermonuclear Experimental...
ETA.
International Thermonuclear Experimental Reactor.
Right. Oh, ETER.
Yes,
Right.
ITER. And this machine is being built in the south of France, and construction is going well.
Right.
And it's truly international. The partnership is Japan, South Korea, the Russian Federation, India, the European Union, and the United States of America.
Right.
And they're all clubbing together because it's very expensive to build.
Yes.
It's going to cost about $10 billion to build. So that's a lot of money for any one country or nation to invest. So it's a truly joint effort to build this machine in the south of France. And scientists will come from all over the world to work on it. The first plasma is due in about 2020.
Right.
And they'll start...
So that's 7 years' time.
Yes.
How old will you be in 7 years' time?
Don't ask me how old I'm going to be.
Nor me. Yes.
And then the first experiments, when they actually use the real fusion fuels, will be in 2025, 2026. And then, instead of not getting out as much energy as you put in, we'll be getting out around about 50 times more or 100 times more.
Right. So it's a bit like putting a gallon of petrol in your car, and you find that your car suddenly and magically has got 50 gallons in it.
Yes, yeah.
So then it becomes really useful.
So you get this huge energy output from it. And how do we get the energy out? Because we've talked about the neutron coming flying off at this height. So you can imagine there's a whole fluence of neutrons coming out of the machine, out of all directions, because they haven't got a charge. They're neutral. They can escape. The magnetic field. The alpha particles have a charge, and they have some energy as well, and they give their energy back up into the plasma. These neutrons come off, and they hit a blanket which is made out of a special metal on the outside of the machine, several meters thick, of lithium.
Right.
And we all know lithium because there's lithium in your mobile phone battery. That's lithium.
Right.
Lithium
lithium
oxide.
battery. Yes.
Yeah, the lithium battery. And this lithium around the outside of the machine, two things happen. When the neutron goes through it, it collides with the atoms of lithium, and it turns them turns them into helium and tritium. And
tritium we used in the beginning.
In the machine. So it makes its own fuel. So the radioactive fuel, tritium has a half-life of 12.5 years.
Yes.
It makes its own fuel to go back into the machine.
So this is like getting your motor car, putting a gallon of petrol in it, and when you look at the petrol gauge, you discover you've actually got 50 gallons, and then as you drive along the road using up your petrol, your car, out of the exhaust, is producing even more petrol. So you see what a wonderful sort of motor car that would be.
Exactly right. So that's a really nice thing about
Yes.
fusion. And so this process takes place, the blanket heats up to about 800 degrees centigrade,
Right.
and then you would just have a heat exchanger in there, boil water, drive
Right.
turbines, and make
And make
electricity.
And the making of the electricity will be producing more of the fuel you need to make the electricity.
Exactly. So the two basic fuels that we need is lithium and water
For the hydrogen.
for the hydrogen.
Right.
So 1 litre of this water and the lithium that's in this, if that was used in a fusion power plant, that would keep you in your energy in Bhutan for around about 21 years.
21, including driving to Paro.
Including driving to Paro, including the boiling your
heating
kettle,
my shower water.
or you're
cooking.
making your car, making the
Right.
television set, anything.
Right.
So
So let's just point that out again. The lithium in a mobile phone battery plus a litre of water, the hydrogen in a litre of water, would provide all the energy I need for everything I do for a month.
no.
Oh.
For 21 years.
For 21 years. Now, if we hold up
Somebody
the
that-
mobile phone, Chris, and the bottle of water, just imagine that what's in there, all my energy needs for 21 years. And you'll see just how important this is. That's an amazing figure. So
So-
can I just recap? In a fission reactor, we get a lot of radioactive waste. And one of the problems, if you are going to close down a fission reactor electricity generating station, the problem is what to do with all that waste. And it's a problem that hasn't really been solved. And as Chris says, the time taken for half of that radioactive waste to decay is about 1 million years. So it's a long-term problem for many, many, many future generations of humanity. But your products from nuclear fusion just
A decade.
a decade.
Decades.
So the problem is much, much less.
And we can recycle them directly
Right.
into new fusion power plants.
Right.
So we would imagine that a fusion power plant would operate for 50 years probably.
Right.
It's something that would be probably the life of the hydroelectric plant as
Yes,
well,
yes.
something like that. So it would operate for that time. Then there would be a short period of it cooling off and everything, but then all of that material could be recycled
Reused.
into a new
Yeah, right,
fusion power plant.
Right.
So what this means, and we've also done a lot in the UK, led a European study into the safety of a fusion reactor, and they looked at all of the possible externalities which might cause a leak or something like that. And there is nothing imaginable except for an earthquake of a magnitude not yet suffered
Right.
that
Right.
that would cause the evacuation of anybody outside the site boundary.
So
So-
if we look at after the Fukushima tidal wave, tsunami and
Yeah.
earthquake, the whole area for miles and miles around that is still not possible for people to go into. But what you're saying is even a force 8, 9 earthquake
Yeah.
would not cause that sort of evacuation.
Because there is only ever a tiny amount of the radioactive fuel on site, and anyway, it's very light. It's helium. It's hydrogen, and it would go up into the upper atmosphere.
Right.
So
Right.
people wouldn't need to be evacuated from around there, and the material itself is solid. It's been
Right, so it's not going to
activated.
go off into the atmosphere.
It's not going to, and it's not got any after heat.
Right.
So it's not going to. It doesn't
Right.
require cooling down.
Right. Well, you know, Chris, thank you very, very much indeed. I said at the beginning that we were going to look into the future. And thank you, Chris, because you've given us an eye into what will be, but it's not just what will be, it's actually happening at the moment. It's proven. It almost certainly will happen. Could you give a very rough guess? I mean, many of our viewers will be teenagers. How old do you think they'll be when we see electricity coming from a fusion reactor? As a rough guess.
As a rough guess, I would imagine that once ITER has demonstrated
Yes.
conclusively, ITER is just bringing together all of the knowledge of the world into one place.
Right.
So, once that has demonstrated conclusively that you can produce more energy than you put in, we will be seeing probably China, Japan will be the leaders. They'll be in the vanguard of building fusion power plants which will generate electricity. And I can imagine that your audience will be in their 40s probably about that time, and we'll be lighting the lights. A friend of mine who is the head of the Chinese fusion program, a guy called Jiangang Li, said to me that was his greatest ambition, that China would be the first. Although, I have to say America and Europe and Russia all have very, very strong programs.
Right.
But perhaps the needs are greater in Japan because they have no natural resources.
Japan has no oil, no energy source
Yeah.
at all. And China, of course, enormous demands for energy.
They're building a power station every 2 weeks.
Yes. A new power station
Every 2 weeks. Yeah.
So, thank you. Now, as Chris has just said, many of you watching this program, by the time you're 40, you will see what Chris has been talking about in this program actually reality in your life. It's almost as if when you were 40, you bought a car which multiplied by 50 the amount of petrol you put in it, and then as you drove it, created its own petrol. Except it won't be a car, it'll be generating electricity. And this project is so interesting because, first of all, it shows how scientific theory and the application of scientific theory, the technology, come together to change our lives. And above all, perhaps, it shows how countries can work together in harmony on a scientific project. Countries which apparently are, if not enemies, they don't particularly like each other, they can work together. And this is one of the wonderful things about science. Science is international. Science brings together people from many, many different countries working on some new project. It's one of the great powers of science. It's an international force. And when fusion reactors are a reality, we're getting our electricity from them, our dependence on oil will be greatly reduced. We'll still need oil to make things like plastics and some chemicals, but oil as a fuel, burning, creating carbon dioxide, making global warming a bigger problem. We won't need to burn oil to create our electricity. So think of the effect on the environment. This will reduce the pollution of the environment very, very much indeed. We won't have to depend upon slightly dangerous nuclear fission generators with all the waste products that they create. So the future for energy lies, Chris, in your projects at Culham on nuclear fusion. And I should add that if you've watched this program, you now know more about nuclear fusion and how far it's progressed than most people in the world. So Bhutan is at the forefront of knowledge in this new future that will affect you all. Chris, thank you very much indeed. It's been very kind of you to give up some time in your holiday. I know you're going on to Parrot Setu, so I do hope you'll enjoy that. Thank you.
Thank you very much, Michael.